Okay. So the first portion we saw some general background on the area, how it's evolved and evolving. We saw the quantum key distribution that's inspired by quantum money, and went into some of the modern techniques for security of quantum key distribution. Some of the questions that I had during the break, I just want to emphasize, like, the sampling is one approach to proving quantum key distribution, and it's actually not the claim to fame of that particular paper. They were really presenting a tool that then has been used in multiple areas. I just thought it was a concept that's relatively easy to grasp, although I admit that I went kind of quickly. It's relatively easy to grasp and then to apply to QKD compared to some of the other approaches that historically were kind of more involved. Okay, so then for on the menu for the second portion, I want to give you some one more really foundational concept of quantum cryptography, which is what you see on the screen. And after that, we'll go into maybe more recent stuff that I've worked on, delegating quantum computations and encryptions and stuff like that. Okay, so bit commitment is it's a building block. It's a primitive, and I will present it here in terms of a situation between Alice and Bob, and it has this kind of physical story that makes a lot of sense. And one thing to keep in mind is when you see these physical stories, then the challenge is to build it using digital encodings. So whether the encodings are actually digital or maybe quantum encodings. And quantum encodings, as a general thread of this presentation, quantum encodings are somewhere in between conventional digital encodings and physical objects. Anyway, so this is a physical situation. Suppose Alice has a bit, and she inserts that bit. She writes it down on a piece of paper, inserts that into a safe, which has a combination lock, closes the door to the safe, and sends that to Bob. This is called commitment, because due to the physical properties, there are some things here that are guaranteed. Namely, once she's given the safe to Bob, she can't change her mind on the bit B. The bit B is written in there, and she can't go and change that remotely. So this is called a binding property. And Bob, from his point of view, the safe is closed. This is called the concealing property. So he can't learn the bit B. The bit commitment has a second stage. It's called the reveal stage, where Alice will reveal the combination to the lock and send that combination to Bob. This is the dial here on the lock, and this represents sending the combination. Now Bob can go and open it. So the concealing is no longer true, but the binding still holds. And so he can open the safe using the combination. So abstractly, we write the exact same thing for bit commitment in terms of some parties and communications and encodings. The importance of bit commitment. Okay. So historically, very early work in quantum cryptography showed that if we have, this is called actually reductions that happen in cryptography, similar to reductions in algorithms. If we have a bit commitment abstractly, then we can use that to build an oblivious transfer. And I haven't defined what is oblivious transfer. We're not going to go into that. It's yet another building block that's even more important. So oblivious transfer, if we have oblivious transfer, then we can actually build all of what's called multi-party computation. So these distributed computations that are secure, we can do that among other things. And this arrow is quantum. So this using quantum communications, we can go from a bit commitment and build an oblivious transfer. Hence the importance of commitment. And this protocol here was also analyzed in different models and more formally in quite a few follow-up works, actually. So the question is, could we achieve bit commitment in a digital world? We've already seen the quantum money. Yay, that's great. Quantum key distribution, that's amazing. We have this quantum advantage. So if only we could have a bit commitment in the quantum world, then we would be able to build OT based on this result, and that would unleash all of multi-party computation, etc., which would have huge consequences. So the history of this problem, and in the context of quantum cryptography, so we had 1984 quantum key distribution, 1992 superdense coding. This is not actually cryptography, but to give you an idea of the stuff that was going on in those days. And then 1993, in quotation marks, provably unbreakable bit commitment. 1995 quantum teleportation. And 1997 impossibility of quantum bit commitment. So these results are contradictory, and we'll go into a little bit of what happened in that time. So this was the paper that claimed the quantum secure quantum bit commitment in 2000. Is that the correct year? Did I say 2013? Wow, I'm really off by decades today. Thank you. Okay, so 1993. So what year is it today? Oh my goodness. Okay, so I actually had the wrong day on my title slide, also, in case somebody had noticed. But that was just off by a day, not a decade. Okay. So this was a paper that claimed to have a secure. And really, their mistake is to apply a classical definition of bit commitment to a quantum procedure. And okay, maybe a little bit like Wiesner, we'll forgive them, although this had major consequences, because and learn from the lesson that when you're devising quantum protocols, you should maybe also rethink your definitions in themselves, and to try to understand, to make sure that your definitions encompass all the possibilities of the adversary. And their mistake was to assume that if Alice can cheat the binding property, then she can simultaneously open both the commitment to 0 and a 1. But that's not required. Cheating binding means that she can decide to her choice which of the two bits she would like to open, 0 or 1. And so that's how you can that's actually the essence of the impossibility proof, is to give a strategy for Alice to decide which one she wants to open. So these were the works that showed the impossibility. So this is a screenshot, so I'm pretty sure I got the date right, and they are the same day. So two concurrent works on showing that quantum bit commitment is not secure. So the challenge, of course, of showing that a quantum cryptographic is impossible is you need to show that any attack will have a decent success probability, so therefore any attack on any protocol, right? No, sorry, that any protocol has an attack. So that's the challenge. And in hindsight, the techniques here used are a quantum version of the classical impossibility of information theoretically secure bit commitment. And if you wanted to do bit commitment with classical encodings, what you would do is, well, Bob would send in a commitment, and then Alice would send a commitment, and then some information about opening it. And by the concealing property, the commitment that Bob receives, whether it's a commitment to 0 or a 1, has to have the same distribution, because otherwise he could tell if it's a commitment to 0 or a 1. But if you have the same distribution, from Bob's point of view, when he gets this, it means that Alice hasn't actually decided what she's sending, whether she's sending a 0 or a 1. It means that after the fact, later on, she can decide to kind of make the message that she sent consistent with sending the bit of her choice. So that's the sketch for the classical impossibility, and I mean, it's maybe not even worth writing down. It's so obvious. The quantum version uses some tools from quantum information theory to formalize the same concept. And it uses the Schmidt decomposition. And this is a special basis that in which we can write any pure state as a linear combination of these Schmidt basis elements, so ket AI and ket BI. So the point being that this is the same index, and you don't have all these cross terms. You can in general write as a sum of AI bj, but if you're in the Schmidt basis, then it's AI bi. Anyways, so there's a corollary to the Schmidt decomposition, which is if you have two pure states, phi and psi, in this bipartite system, A tensor B, and suppose that you have exactly the same reduced density when you trace out the system B. So on system A, phi and psi are the same. That means that there exists, by this corollary says that there exists a unitary on the system B only that will map psi to phi. So that's what we're going to use to break any generic bit commitment scheme. So the theorem is that there's no perfectly concealing and perfectly binding quantum bit commitment protocol. This sketch can also be expanded to epsilon binding and delta concealing. This is the binding and the concealing properties that we've mentioned already. And the proof is by contradiction. Suppose you had such a scheme, and then we can do this purification. So any scheme might include measurements or non-unitary maps, but mathematically we can purify that and make them unitary. And so we purify the protocol, making it therefore make it unitary, so we always have pure states. And then after the commit phase, there's two possibilities. If Alice had committed to 0, then the joint state will be psi 0. If she had committed to 1, the joint state will be psi 1. By the hiding property, Bob cannot tell whether the commitment is to 0 or to 1. So that means that the reduced density on Bob's system have to be the same for this perfect situation. And then we apply the corollary, meaning that there's going to be a unitary on the A system only that will map psi 0 to psi 1. Oh, but that gives us an attack for Alice. That means that she can completely break the binding property and decide after the fact what was the bit to which she had committed. And as I mentioned, we also have a generalization to the approximate case. So quantum bit commitment in the information theoretic sense is not going to be realizable using quantum communications only. It's still a possibility to consider quantum bit commitment, and we can build it using extra assumptions. So one assumption will be a computational assumption. This is also what happens classically, and it's possible to have a statistically binding and computationally hiding bit commitment, or the other way around, computationally binding, statistically hiding. So computationally, when I say computationally hiding or binding, it means that that property only holds against computationally bounded adversaries, meaning that we've assumed that, for instance, the adversary cannot break some underlying assumption, whether it be a one-wave function or something like that. And then there's also physical assumptions, and this has been a very productive model, especially for quantum. So there's a concept called the bounded quantum storage. And this is where we assume that the adversary has limited quantum storage. This is relevant because actually today quantum storage is almost non-existent. So if we're willing to suppose that the adversary has only so much more storage than the honest parties. So usually these types of protocols require no storage for honest parties and are secure against adversaries that have only polynomial quantum storage. So that's called bounded quantum storage. There's another one called noisy quantum storage, which is related, which is that it's not possible to perfectly store quantum information. It's going to become noisy after a certain time bound. And there's another model in which we can also get quantum bit commitment that's isolated qubits. So that means that we limit the multi-party or the multi-qubit operations, and that's basically a physical assumption. And based on that, we can also get some interesting cryptographic things related to bit commitment. And for more details, I'll refer you to the survey that I had already mentioned. Okay, any questions about the quantum bit commitment?
Yeah, very small question. Could you mention what statistical means there, like statistical hiding and statistical binding?
Ooh, thank you. So, okay, so statistical is a synonym that I used for information theoretic. It's slightly more, um, okay, they can mean the same thing. They can mean exactly the same thing. Statistical emphasizes that there could be a slight statistical deviation, but we're talking about uh, indistinguishability or whatever it is, hiding in the sense of information theory or statistics.
A quick question as well. Maybe this is a silly one. Just clarify, in quantum bit commitment, the committed thing is still a classical bit, or is the quantum state?
Oh, that's a good one. So, a big asterisk to anything you read with the title, it says quantum X. It's impossible to know without reading the details or if you know the background, if they're talking about a functionality for the quantum data or if they're using quantum to build the classical functionality. So, for this situation, it's for a classical bit, just as in the classical case, and we're going to use quantum to do it. So there's actually a famous, I don't know, an example I like to give is like quantum multiparty computation. Totally not clear if it's for computing quantum stuff or if it's classical multiparty computation using quantum. So no, definitely not a silly question.
As a follow-up, so if classical is a subset of quantum, I think I'm a bit confused about how quantum version is impossible, but classical is. Like, can't you just do classical operations?
The classical bit commitment is also impossible.
All right.
Okay, so let's talk about delegated quantum computation. First of all, what is this delegation business? So we're going to talk about a client. Sometimes we'll call it Alice, and a server or a cloud. Sometimes Bob. And the idea is that one of them is powerful, namely the server, and then the other one is less powerful. And you can have, okay, as I said, a cloud. For a very simple picture, imagine that you're delegating your storage. So you send your data to the cloud, and in the future time, the cloud will maybe return your data. Okay. Maybe you want to take advantage of the processing on the cloud. So for email, for instance, you might want to search your email, so the server would return the function of the data. This immediately raises some privacy concerns, and maybe if I mention the next application, maybe like online income tax software, I don't even know if you need to go, like even the first and second applications, would you be able to encrypt your data and take advantage of the remote storage or quantum computing or computing capabilities? Okay, so a private computation would look like something like this. We will encrypt using an encryption scheme in a key K. The key stays with the client, and the encrypted data goes over to the server. And then maybe we want to compute a function. Well, okay, would it be possible for the server to compute a function on the data itself and return it and return that in an encrypted form? This is very counterintuitive because when you think about it, the cloud is getting stuff that's incomprehensible. Okay, by definition, it's encrypted. So how could it possibly compute on that data so that all the client would have to do here is decrypt? So because of this form here, it means that the client, knowing the key, could actually decrypt, apply the DEC operation that would reveal the function applied to the data. And this is a question that was brought forward 1978 by this paper by Revest of RSA fame. Adelman and Dertuzos. And so in their introductory paragraph, they talk about the fact that encryption, basically they said they bring up this point that encryption limits the information. So how could you possibly apply any more complicated operation, such as a computation? Any more complicated operations seem to require that the data be decrypted before being operated on. Well, is this the end of the story? No. We can already see, if you know about how we encrypt using the RSA public key encryption scheme, it has to do with modular arithmetic. And in the plain version, well, if you have two ciphertexts, so actually the encryption is done by raising to a modular exponent, raising to an exponent, modulo m. If you have these two ciphertexts, you can actually multiply them together, and then that's going to multiply the plain text. So that's as if you had multiplied the plain text and re-encrypted it. So we say that RSA is multiplicatively homomorphic. Homomorphic means that you can do the operations under the encryption layer. And this was an open question for a long time. Can we have fully homomorphic encryption, meaning that we can do both multiplication and addition? Since multiplication and addition together are a universal circuit family, then that means that we can do any function. So this was a breakthrough result in 2009. So all of this is classical, but we can apply the same logic and ask similar questions quantumly. So in the quantum case, we'll have a quantum server, we'll have a client. It's computationally weaker. And for an application, maybe the client wants to delegate Shor's factoring algorithm without revealing what public key they're trying to factor. So therefore, without revealing the identity of the person that they're trying to compromise. So maybe you'd want to process quantum data by the quantum cloud, such as processing quantum money, which is an application that we saw previously, like to verify quantum money using the remote quantum computer. And so given the current challenges in building quantum computers, we really expect, and this is the current business model of all the quantum computing companies that I know of, or the main business model, is to commercialize remote cloud quantum computations. So, and then on the other hand, from the point of view of the clients, we're in the situation of a race and competitive advantage in finding new quantum algorithms. So the client will want to maintain privacy of what's the algorithm that they have come up with and they want to run on the computer, and or if they're processing a private data, so if you're in some healthcare application, for instance, and you need to, you're only allowed to upload encrypted data, could they upload the encrypted data and take advantage of the remote quantum processing power of the quantum cloud? And for the situation we're going to look at right now, we're going to look at information or statistical, used as a synonym, security. The situation is going to be interactive, so we're going to allow some interaction between the client and the server. And the client will be almost classical. We'll allow the client to prepare random qubits, which are the same here as in quantum key distribution. And this is the approach that we're going to follow. There are others, namely, you may have heard of blind quantum computation, which was a precursor and which was developed in the circuit-based model, no, in the measurement-based model for quantum computation. The one I'm going to present here is in the circuit model. So, fortunately, we've already introduced the one-time pad encryption scheme. We're going to generalize it to the quantum case now. So if you have quantum data, here I'll represent it as a single qubit pure state as this superposition, alpha 0 plus beta 1. The key in the quantum one-time pad, so now I mean a functionality for quantum data. So you want to encrypt a quantum state. You need 2 bits of key. It'll be A and B. And it turns out that if we apply this random poly, so z to the a, x to the b means that condition on the value a and b will apply one of the 4 polys, identity X, Z, or both, which ends up being Y. So mathematically, you can show that if you take the mixture over all possible keys, then the resulting ciphertext is a maximally mixed state, meaning that it's independent of the message. The protocol for computing unencrypted data at a high level looks like the following. Alice has a state rho that she encrypts with a one-time pad. And in this cartoon picture, this is the hypothetical circuit that she wants to get the remote quantum cloud to execute for her. So instead of sending rho itself, she sends the encrypted version. The keys here are these exponents, A1, B1, A2, B2, etc. And then the server knows, in this situation, the server knows the quantum circuit that they're supposed to do. They're going to go into gadgets. And at a high level, for at each time slice, if we were to decrypt on the wires, we would obtain the same wires had we done the computation on the plain text itself. So we keep that invariant, and we go through different gadgets. So the T gate is going to apply something, and it's going to always guarantee this invariant. And this will be the key, the updated key. So Alice is going to know how to update her key based on the gadget that they just did, and possibly based on the interaction. So we're going to have different gadgets for different gate elements. We'll talk about the universal gate set shortly. Et cetera, et cetera. And at the end, as usual, Alice knows this key here that she has updated as they're going along, and she receives the quantum output from the server, and she can decrypt it. Or if the output is actually classical, and this is kind of interesting, then the server can measure it for her, and then her encryption key, she only keeps the X component of the encryption key because the measurement is just going to obliterate the Z component of the state. So how do we do this? Here are some simple elements. So if there's a single qubit preparation, then Bob should just prepare it, and Alice should set the key to 0. If there's a measurement, as I had just mentioned, Bob should measure that it's always going to be in the computational basis, and then the key corresponds to just the X component of the key. So for our gate set, we're going to use the Clifford gate set, and then we're going to augment that to make it universal. The Clifford group is the set of operations that conjugate poly operators into poly operators. So that's really convenient. It means that if you apply a Clifford gate on a wire that's encoded with a poly key, then all you need to do is to update the poly key based on the conjugation equation. And it's as if you had applied that exact same Clifford on the unencrypted data. Okay, so here's the examples. Okay, X is very easy. If you're coming in with an encryption AB, you apply X, then the decryption is the same. Z is the same thing. Hadamard, so you know HX equals X ZH. So the Hadamard swaps the roles of the X and Z keys. The P gate does something to the B component, to the Z component. And this is how you should update the key for the C0. If you know about stabilizer formalism and stuff like that, this is all related. So to get universality for quantum computations, we need to add a non-Clifford group gate, and we'll use the R gate. Okay, these slides for historical purposes talk about R gate, and a little bit later it's going to become T gate. Turns out that for a while the community hadn't really collapsed or converged to a convention on what we're going to call this gate. It's also called the Pyra 8 gate, and now it's kind of T gate. Okay, but at that time it was some people call it R. It turns out that if you apply the R gate on something that's encrypted with a poly, of course this is a non-Clifford group gate, you're not going to get a simple poly update. What you get picks up this P to the A, where P is the gate, this phase gate described in the previous slide. So if A is equal to 1, you have this unwanted P error here. If A is equal to 0, then you don't have that unwanted P error. And the main idea is that we're going to, the client is going to, if only the client could tell the server, hey, A is equal to 1, please apply a P gate to undo this, then we'd be good. But we can't tell the server what the key is because that would compromise the privacy, of course. So we're going to go into a gadget, a sub-procedure, that's going to get the server to apply the P correction without the server knowing that they've applied the P correction. And this is what it looks like. Let's go through it. The top portion is the wire belonging to the server. This is the qubit that's encoded here coming in. And then this protocol is going to have auxiliary qubits and classical communication. Double wires are classical, single wires are quantum. So the server does that OR gate on the encrypted data. So that's going to have this effect here of having this P to the A, possibly, based on A. Okay, so the client prepares an auxiliary state, and this is a plus state that has a hidden P to the Y. So Y is random, and somehow it's encrypted by this Z to the D. So all of this is in the single plane, and so you don't need an X encryption to encrypt this state. And yeah, you should think about this as a hidden P. So the server can't tell whether the P is applied or not. And these are the 4 possibilities for these states. The server then does a control knot that basically entangles the data wire with this auxiliary wire that it's received from the client. So this wire goes through this dashed line, meaning that the server now has this qubit. The client also sends a classical bit, X. And X is the XOR of A and Y. A is the secret that we definitely do not want to reveal. Y is whether or not there's a hidden P here in this qubit. So a Y is a little bit acting like a key in a one-time pad to hide A, but Y also appears in this qubit. So this classical bit here is sent to the server and then controlled on this classical bit. The server is going to do P to the X. Remember that we wanted the server to do P to the A, actually, but we don't want to reveal A. So this is the next best thing because the net effect is that it's going to apply this P correction if and only if A is equal to 1 up to some key updates that the client can do because the client knows Y, D, A, and even this classical bit C, which is obtained for the measurement. So at this point, the top wire is measured. This is a little bit of a gate teleportation type of thing, where this measurement result here, C, is actually uniform in the honest case. It doesn't reveal anything about the data, which is great because it means that this bottom wire here can, and it actually does, contain the output of the computation. So at this point, you should kind of logically swap in your mind where does the data, what wire continues through the computation, and it actually becomes this bottom wire. This auxiliary qubit becomes the wire that continues in the computation. So given this C, this client actually has everything required to update the key, and it turns out to be this formula here. So for correctness of this T-gate protocol or the R-gate protocol, maybe I'll just flash this on the screen. It uses some circuit derivation techniques inspired by some early work on making links between teleportation and measurement-based quantum computation and circuit-based computation. And so we can transform like simple quantum circuits that are known. This is the type of it's called X teleportation. And then you can transform it using some different steps here and properties of how the gates propagate basically over the control knot and how they behave with measurements. And then using some links between, some just identities that are true up to some phases, then we can compute the final decryption key that Alice should update. So the idea in that is that we can substitute this sending the value A in the clear with quantum communication and classical communication and keep it secret. For the security, I wanted to mention how we could hope to define security for this delegated task. and an idea of the proof sketch. So we want to argue that the server doesn't learn anything about Alice's input. In other words, that it's encrypted. And remember when I said, oh, not learn anything, that needs to be made formal if you want to have a formal quantum cryptography paper. So one of the models that's been very successful for formalizing what it means to learn no information is the simulation paradigm. And this is what we use here. So we model, and also called the ideal versus real world. I mean, there's lots of details in what I'm saying at a high level here. What we model is the input coming in, possibly entangled, and between the client and some auxiliary space, which we actually give to the server to be as paranoid as possible. And the C space is going to be used by the client as the input for the computation, and the S space is going to be given to the server. And suppose S prime is any deviating server, so it can be doing anything here. We want to argue that the server can't learn any information, whatever that means. So let's define that. We'll talk about a simulation world. In this world, the input C goes straight to the garbage, and the auxiliary space S goes to the simulator. The simulator knows a description of S prime, and its job is to output something. And these two pictures define quantum channels, right? Because they have an input here and an output, phi and psi, these two quantum channels. We'll say that the protocol for delegated quantum computation is secure if for every S prime, so deviating server, there exists a simulator S sub S prime such that these two channels are indistinguishable. That means that whatever attack that could be mounted in this real world, the simulator could also mount an attack in the ideal world. But in the ideal world, the client's input doesn't even exist. It's been thrown in the garbage. So this one is secure by definition. And since the real world is close to the ideal world, and the ideal world is secure by definition, it means that the real world is secure. That's the basic idea. And this indistinguishability is formally defined by Diamond norm. We actually don't need to go into the details. Just think about them. Just think about it as an adversary. Yet another adversary cannot tell whether they're given access to the first or the second channel with one-shot access. The proof outline for this delegated quantum computation scheme is inspired actually by what we saw in the proof of quantum key distribution, where we go to a purified situation. What would it mean to purify the initial protocol for delegated quantum computation? Well, we're going to go through different steps where we modify the starting protocol such that the server cannot tell that it's being modified. Yet at the end, when we've done all the modification, the protocol is trivially secure. And the idea is to use entanglement. Entanglement is often used in quantum cryptography as a thought experiment. We can write down mathematically the same protocol that we're looking at, but we emphasize the entanglement in it, and then we argue mathematically about that entanglement, and that enables us to deduce the security of the original protocol. So that's what we saw actually in quantum key distribution. We'll use that here too. So instead of sending encrypted qubits, the client can send half EPR pairs. A maximally entangled state is half of it. Maximally mixed state is half of an EPR pair. So, and in fact, if you look at the quantum one-time pad encryption scheme, you'll see lots and lots of links with maximally entangled states. So we'll take advantage of that. And then instead of sending auxiliary qubits whenever we do a T gate or an R gate, the client is going to send half EPR pairs, and we'll have a sketch of that coming up. And also, via these pairs, we can actually get the client to delay using her input until after the protocol has been delegated, until after the computation has actually been completed and she's received all the inputs from the server. That means that the input itself didn't even have to exist while they were executing the protocol, while the server was involved, meaning that the simulation is going to work just as well as the protocol in the real world. Here is the version of the R-gate protocol where we use entanglement instead. So the auxiliary qubit is going to be a half EPR pair. And what the client can do is delay her choice of the basis until after she's sent this half EPR pair. And similar to the proof of quantum key distribution, this will have the effect of preparing the auxiliary state on the server side. And we'll do this for all the qubits, and the server's point of view is completely unchanged. And similarly for the, this slide was actually for encryption. Okay, it's a little bit hard for me to read from the side. So this was actually for encryption. This is even simpler. So sending an encrypted qubit is like sending in a half EPR pair. For the R-gate gadgets, we do a little bit more complicated, but basically the auxiliary state is also a half EPR pair, and Alice delays her measurement here to her value D, which was previously chosen by her at random, is now chosen by the measurement of the half EPR pair. And similarly, the bit here can now be uniform to start with, and then she'll adapt for that later by choosing a different value here of Y. And we'll do this for each R-gate protocol. And we can always delay these portions of Alice that have to do with measuring the half EPR pairs. We delay that to the very, very end. And that's how we'll get the simulator, which is obtained by delaying all these things in the real world. And then we don't actually need the input here. We can throw it in the garbage. And at each step, we've argued that the point of view of the simulator is the same. So that means that the two channels are actually not just close, but they're actually identical. So we've shown methods to compute unencrypted data. What we haven't shown is how to know that the outcome is correct. Okay, so those are two complementary requirements. When you think about it in the quantum case, it's very relevant, even classical case, it's very relevant to be able to know that the outcome is correct. So you might not trust, you don't trust the server with your private data, but you maybe not even trust the server to do the operations that you've asking them to do. So how could you know? Well, so far, a lot of science progress has followed this cartoon version of the scientific method. We postulate a hypothesis. Based on the hypothesis, we make predictions. So we expect to observe such and such thing, and then we do some experimental verification that that thing happens for real. So this is a problem for quantum computers. Namely, we are building quantum computers because we think that they are more powerful than classical computers. That means that we are running experiments that we expect are not able to predict the outcome of those experiments, because if you could predict the outcome, you're not going to build a quantum computer. You don't need it. So for large-scale experiments, at least, we needed an alternative to this predict and verify paradigm. This is really a fundamental problem. It's very interesting. Fundamental problem that arises from this quantum computing paradigm. So you might come up with some ideas of how we could get around this barrier. Maybe we could test small parts. So if you're trying to build a large quantum computer, you'll test like small components and verify that they work as expected. And then when you go and run a larger quantum computation that uses all of the components at the same time, you'll somehow assume that they work correctly together. This is an extra assumption, the assumption that when you run the larger quantum computation, the smaller parts continue to behave the same way. And we don't want to make this an extra assumption like that. Maybe you could test computations that are easy to verify. So for instance, factoring. If somebody builds a quantum computer and factors, then the verification procedure for factoring is to multiply the numbers. So you get n, p, and q, and then you multiply them together. And if you get your original input n, you know that the outcome is correct. So that's very fortunate for factoring. Unfortunately, it's not the case for the hardest quantum problems. They're called BQP complete problems. And we don't know of any efficient way to verify them. One, approximating the Jones polynomial is BQP complete. Another example is to simply, given a quantum circuit, to decide whether the quantum circuit outputs 0 or 1 if you're going to measure one of the output qubits. So given a generic quantum circuit. So this is the problem that we're going to look at in, since it's a generic case of the hardest quantum problems. To get inspiration for a possible solution, let's look at what it means to prove something. Probably the type of proof that you have in mind, if we're talking about proving, is a static proof. It means that it's something that you can write on a piece of paper and somebody else can verify, such as claimed factorization of a large composite number. The question is n, the composite number, and the answer is pq, and then this could be verified offline. Yet there is, an NP is a class of languages that have such a static proof, MA if you're talking about probabilistic verification. So the question is, could we verify more than MA? And for inspiration, let's look at complexity theory. And it's been known for quite some time already that interaction increases the power of the verification process massively. Okay, so if you have anything that can be computed in polynomial space, which is very large, it's called p-space, can be proven in an interactive process. So what's an interactive process for verification? It means that a verifier talks to a prover, discusses back and forth, and basically asks challenges. The verifier can maybe compute simple stuff on their side, but keep some secrets from the prover, and based on that can gain confidence in the answer that the prover is providing. This is the interactive proof model. What we're doing for delegated computation is slightly different. In the interactive proof model, we have a polynomial time verifier and an unbounded prover. For quantum computations, we'll want a quantum polynomial time prover and a classical or almost classical polynomial time verifier. Okay, so that's what we're going to do. We're going to go interactively. So the concept is that as the experimenter, you can verify and characterize very simple quantum systems. You can predict the output of trivial quantum computations. So for instance, if I ask you to predict the output of the identity circuit on the input 0, although maybe this is a polynomial quantum computation, then you know that the output is also 0. And you can interact with the setup. So the idea is that we'll take this small quantum capability from point number 1 together with 2 and 3, and we'll bootstrap that into verification of general quantum systems, or quantum operations, I should say, maybe. Any questions on the paradigm so far?
Was it considered for classical computers when they started, or down along the road? Was it like, I think you could say that the same scenario happened when we started using the classical computers. Why should we trust them for calculations we cannot do by hand?
Yeah, I wonder that. I've tried to query like some of the people whenever I meet somebody who's been in computing for some time. What did I find out? I don't remember. I think they thought, oh, we'll just repeat. But I wasn't quite satisfied with that answer. One thing is that there is some recent theoretical work on a delegation model where you have a weak classical client and a classical polynomial time quantum computer. It's called Interactive Proofs for Muggles, from the Harry Potter Muggles. And I think it was like a log space verifier and a regular prover, something like that. Yeah, if anybody has more anecdotes about verification in the early classical days, I'd be interested to hear. But I think that the quantum adds really like a level of complexity that's like different from classical. So maybe you're willing to accept the repetition for classical, but quantum just I'm a lot more skeptical for quantum, let's say. So the idea, we're going to have interaction and we're going to use cryptography. So this is really nice. We get to use the hiding property of computing on encrypted data, quantum computing on encrypted data, to do two things. Well, we could be doing test runs, which are testing that the computer is running honestly or almost honestly. Or we could be doing computation runs. And these ones are doing something for which the answer, we're really interested in obtaining the answer. And by the cryptography layer, the prover will not be able to tell if it's being tested or whether it's doing computation. When you think about it, if you're in an interactive setup and you can't tell if you're being tested or being honest, you should be honest, because otherwise you might be detected. So it's exactly the same principle. And we're going to have two classes of provers. We could have a benign prover. Benign is, it may be deviating, but that deviation has no effect on the output of the computation. So we're happy to accept benign provers and trust their answer. Or a non-benign prover has malicious behavior that could compromise the output of the computation, and we will guarantee via the entire construction that a non-benign prover is detected in a test run. To give you an idea, not going into the details necessarily, we adapt the T-gate gadget. So in the quantum computing unencrypted data, we want to hide the data and compute on it, even though it's encrypted. Here, we want to do a T-gate gadget from the client's point of view, and the server should not know whether they're computing on the test run or a computation run. So in the computation run, we're computing unencrypted data, and here, it's slightly different. The client is going to do the T-gate themselves on the auxiliary state, send it over, and then the server entangles as a measurement, returns the measurement, and there's a key update. The reason we do this is that in the X test run, the server should do exactly the same thing and see exactly the same thing. So they do exactly the same operations, and they also see an encrypted qubit, except in the X test run, the qubit is an encrypted 0. And here the client does some stuff that is preparing stuff that is a random, yet is not sufficiently random in the sense that this is going to do compute a identity on the 0 up to some change of key, plus the measurement result from the X test run here that the server would be doing has a deterministic outcome. It should be A XOR D. If it's not A XOR D, it means that there's been a deviation in this benign in this non-benign situation, and the client should definitely reject. For technical reasons, there's a Z test run, but I don't even want to get into it. So for this one, I'm not going to go into the definitions or the proof. The proof uses EPR purification. Big surprise. So what we've done is using interaction and some quantum qubits sent by the client, we're able to delegate this quantum computation in a verifiable way. You could ask, okay, could we make the client completely classical? So no quantum power at all. And this question has been looked at from two angles. We could ask about a classical verifier by making computational assumptions. And if you're willing to make computational assumptions, this one is the existence of claw-free trapdoor one-way permutations, if I'm not mistaken. We can follow Mahadev and follow-up work that delegates quantum computations verifiably. Completely different paradigm, I should put a line between these two, is to maintain the information theoretic or statistical properties and no computational assumptions, yet a physical assumption here that the client can interact with two separate isolated quantum servers. And namely, the servers could also and do end up needing entanglement. So this was a breakthrough by Reichardt, Unger, and Vazirani, who showed how in this situation, we could take advantage. So it's a little bit kind of like cross-interrogating two suspects. So if you have the benefit of having two suspects and being able to ask them questions without them being able to coordinate their answers, maybe you can squeeze them into revealing something because of their separation, you can like ask them questions to trick them, not necessarily to trick them, but to learn information and to check if they've been really honest or not. The technique of Reichardt, so yeah, I want to focus on the right-hand side, not necessarily, and not go into the computational version. The technique on the right-hand side is to, in a very elaborate way, intermingle a non-local game. So if you've heard about this CHSH inequality or Bell inequalities, magic square game, or anything like that, non-local games, which could be actually a good topic of an entire QIP tutorial, you can intermingle the non-local game, which are challenges, classical challenges that Alice and Bob must respond that require entanglement in order to win. So you would intermingle that with a computation. So similar to the other situation where we had the test run and the computation run, except here the test is to play these non-local games. And there's some property called self-testing, which is that if the verifier observes, and it's a property of certain games, if the verifier observes an optimal winning strategy or close to an optimal winning strategy, then the verifier can actually deduce that the provers are playing that optimal winning strategy up to some mapping that's well understood. So therefore, what the verifier does is hides whether they're testing using a non-local game or whether they are doing the delegated computation or the proof verification. And this idea has been of self-testing has been very prolific as a tool in quantum cryptography and beyond. I wanted to mention this work of Caldangelo, Grillo, Jeffrey, and Vidic, who combined the how to verify a quantum computation that we just saw with the X test, Z test, and computation runs with a non-local game, namely the Magic Square game, put those together and were able to delegate a quantum computation with a classical client and two provers. And in this case, they got parameters that were better than the previously known results. The protocol, nevertheless, requires multiple rounds of interaction. Follow-up work by Grillo was able to make the first protocol for delegated computation in one round. So one round is particularly relevant as this is also called a relativistic protocol. And the reason is that when I said that the provers are separated, cannot communicate, well, how do you enforce that? You could try to put them in like some sort of cages, Faraday cages apparently, they don't allow communication. But really the only way to be totally sure is to use the limitation on the speed of light and the fact that and the timing of the messages. So you place Alice and Bob, Alice and Bob will be the provers, far enough away such that when you calculate the time that you send the question and the time you get the answer to conclude that there was no physical way for any signal to transfer from Alice to Bob during the time that they had received and sent back their answers. And a one-round protocol will fit in that model, and that means that you can implement this situation a little bit more realistically. And I'm not going to go into the details really, but Alex Grillo found an alternative to the circuit-based situation where, in the circuit-based, well, when you have a T-gate, you have these poly corrections, and you need to do something to get through that. And so far, we had done that with interaction. So he has a different way to kind of represent a verifiable quantum computation. And thanks to that and some intermingling with a non-local game, he gets the delegation. So yeah, emphasis here on one round. There's another property that you might want to have in delegated quantum computation protocols, and it's called zero knowledge. Zero knowledge is a very counterintuitive property of a proof system that it's possible to convince somebody of something without revealing any information about that something. Yeah, it's super counterintuitive. It's like as if I'm marking an exam and I can decide that the exam is correct without knowing anything about the student's answer. To give you an idea of maybe why this is possible, here's a little example. So where's Waldo, as it's called in North America? I think it's Waldo has different names based on its geographic location. Charlie in France and Wally in the UK. Yeah. Okay. So suppose that I know how to find Waldo, and I want to show you that I know where Waldo is without revealing further information about where Waldo is himself. So I actually have a physical demonstration of this that I didn't bring today, but I have this large sheet of a little pinhole in it, and so I will place the book just behind the sheet, and you'll be able to see Waldo through the pinhole without knowing anything about the context of where he is. Okay, so some people have found him. So here's my digital representation of that. The pinhole is a little bit too large, but I will show you where Waldo is without the context around it. So okay, so maybe zero knowledge is possible after all, because this is very, we're kind of solving this counterintuitive situation, at least for where's Waldo. Zero knowledge for quantum computers has this extra interest that I only realized this recently. Actually, I went to the quantum cybersecurity workshop by the U.S. government, and they were talking about preventing reverse engineering of quantum computers. So. Oh, okay. Well, reverse engineering is learning things about the inner workings of the quantum computer. And a zero-knowledge proof is exactly that, is proving something, revealing the answer without saying how the answer has been computed. So I'm optimistic that we'll be able to take advantage of zero-knowledge proofs to protect the intellectual property and trade secrets of our precious quantum cloud servers. Okay, and how do we do that? A really nice technique is called simulatable codes, and this is a quantum code that has a really interesting property. So what you do is you take something that's hard to come up with, such as a witness for a QMA complete problem, or maybe a Hamiltonian of that Grillo had for his way to verify a quantum computation, and you encode it in this code, and the code has a property that locally, where did I write it? The reduced density tau sim on any small number of qubits is easy to compute. So that means that if you only have small snapshots of that encoded system, those small snapshots themselves reveal no information because they're easy to come up with. In other words, they're easy to simulate if you're going back to that simulation paradigm terminology. There's no classical analog of this. If I tell you that I have a classical string and each substring on, say, a constant number of qubits is easy to describe, then the entire string is also easy to describe. Namely, you'll just get all the small portions and concatenate them together. Quantumly, it's a completely different situation. Small snapshots are reduced density matrices, and reduced density matrices do not describe anything about the joint entanglement of the larger system. So going back to my fruit, apple slices themselves don't tell you anything about how to put back the apple slices to get the apple. This is an Apple computer. Okay. And that's the first time I noticed that. Okay. So that's the paradigm of the simulatable proofs, and we can use that for zero knowledge because when you think about it, small snapshots, maybe a small snapshot is good enough to verify a proof, but we're saying that it's not good enough to like construct the entire proof. Anyways, those two statements seem very contradictory. It turns out there's a way to put them together and make it work, and that's what. We did with Arthur Mehta and Yubing Zhao here present. And we basically, in a snapshot, made the griddle protocol zero knowledge. So now we have a relativistic protocol that is also zero knowledge. So you can do this in one round of communication. It doesn't reveal anything about the inner workings of the quantum computer. Quantum computers, because we have two provers, and it will be a whole other talk to talk about the mathematical techniques that are pretty involved. When you think about it, you need to kind of how do you say consolidate the zero knowledge property, which is that you should learn nothing, with the verification property, which is you should know no fake witness to be able to pass this verification. Let me see. So let me take questions about delegated computation and encryption and verification and stuff like that before moving possibly to another topic.
Maybe I missed this, but what's the comparison between classical homomorphic encryption and quantum homomorphic encryption in the sense of, can I use the quantum server to do classical computation on it, but the advantage is that due to some quantum effect, it's impossible to read off the data that I'm doing.
Yeah. Yeah, thanks for the question. I hesitated to start with the homomorphic thing because then I kind of diverged and didn't continue on the homomorphic side. So there is a quantum homomorphic, which I didn't talk about. The big distinction in homomorphic is that the server should be able to choose the circuit that they want to do. In the ones that I'm talking about today, the client chooses everything, the data and the computation. Yet your question is applicable also to the delegated task that I talked about today. So it's about classical being a special case of quantum. Is that right? I think I've diverged.
Yeah, so I guess to make things more concrete, like in the sense of like medical records. So if I want to send medical records like AWS, I could use like I could delegate it classically, like use a classical algorithm to hide the data, like encrypt the data.
Okay.
Yeah.
Okay, so you could use a classical algorithm to hide the data, but that classical algorithm, if say you use classical fully homomorphic encryption, definitely does not allow quantum computations on the data. So presumably the AWS is going to do a quantum computation, which is why you're using it in the first place.
Okay, so it wouldn't make sense for me to. It wouldn't make sense for me to use a quantum computer to do classical computation just to.
Correct.
Okay.
I would not recommend that.
Maybe I missed something, but how the success probability of non-local game impacts on this delegated quantum computing?
Ooh, okay. So how does the success probability of the lots of details were completely glossed over, and definitely you need to have your robustness parameter for the non-local game, and that's going to feed into the soundness of your proof system.
Okay, thank you.
Okay. I'd like to tell you about certified deletion as my final topic. And let's go back to this picture of a safe. And this time we're going to do something different with the safe. Alice puts a message, writes it down on a piece of paper, and she sends it to Bob. So far it looks a lot like the bit commitment. Except at this point, we'll do something different. So Bob, he could decide from his own, based on whatever he likes to do that day, he could return the closed safe before the combination is revealed. So Alice has the intention of eventually revealing the combination. Why the combination would be revealed? That's a design choice. It could be like eventually some sort of public key is broken, or it could be by design. Eventually, Alice is going to reveal. So he could return the safe. As a kind of proof that he's returned it. And the idea is that if he returns the safe, he's never read the message, he never had the combination. XOR, he could keep the safe, and when the combination is available, open it and read the contents. And I really mean exclusive OR in the sense that when you go to the restaurant and they ask you, would you like soup or salad? They mean soup XOR salad. Okay, one, the other, but not both. So he can do this or this, but by the physical property, there's only one safe, so he could return it or keep it, XOR keep it. Could we achieve this in a digital world? So could we have this type of returning of the safe where the encodings are classical information only? And the answer is no, and it's a very simple argument. So suppose there was a way to encode a message. This is a classical encoding using a key K of a message and send it to Bob. And suppose it does have this deletion property, which I haven't formalized yet. He could convince Alice, wait a minute. Yeah, okay, so there's these two properties that aren't written down here, but when he returns the safe, he convinces Alice that he's returned it, and he has no access to the data. When he keeps the safe, well, he'll be able to decrypt. Okay, so he can convince Alice that he did not read the message by returning copy number 1. Whichever way, it's a hypothetical proof. So suppose that this is secure, then use the first copy to apply this procedure to return. And he could use the second copy to use the combination that's eventually revealed to open and read the contents. So because of copying, notice that here we have a copying operation, that Bob has been able to accomplish these two concepts. So thinking classically, you would never really come up with certified deletion, or if you did, you would immediately realize that it's trivially impossible to accomplish this using classical encodings. And so we call it certified deletion because when you go here and return it, it's like a deletion. And actually we'll see in the quantum version, it actually is deleting. It's not just returning the safe, it's proving that you've blown it up. Okay, so here's an application. Alice has her last will and testament that's stored safely at the lawyer's office. And suppose that one day something happens and Alice realizes, wow, okay, I absolutely need to delete that will and to make sure that nobody ever sees it. And please, 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 let's go to the office and make sure that the lawyer has deleted it and not kept any backup copy. So if she stores this with certified deletion, there would be a way indeed for the lawyer to prove that it's been irrevocably deleted. And then she could proceed to update it to a new one. In quantum encryption with certified deletion, it's yet another situation where quantum mechanics is going to give us this best of the both worlds, of the physical world that has these cryptographic properties, such as the safe that you can only have, for which you can only have one copy, and the digital world where you can use encodings and process information kind of digitally. And furthermore, as I alluded to, in the quantum case, the proof of deletion will not be returning the quantum state, is going to be actually creating a classical proof that the message has been destructed. And here's the scheme using an example. It's pretty easy to generalize it based on this this situation. So suppose that we're going to have an encoding that consists in 4 qubits. So the first step is to create Wiesner conjugate coding states. We've seen this over and over again. These conjugate coding states really have this no cloning / complementary bases that are just perfect for a lot of these cryptographic applications. So we'll choose a random basis. This is Alice. Choose a random basis theta, a random bit string R. This was called B previously in some other applications. And then we'll get the Wiesner encoding R sub theta, which gives these 4 qubits. Based on these choices, we define some substrings. So R sub comp is the R string where we select only the bits that are encoded in the computational basis, so where theta is equal to 0. So this will be the substring 0, 1, and R diag is the complementary substring 1, 0 here, where the qubits are encoded in the diagonal basis. And whether the qubits are in the computational or diagonal basis make a big difference here for certified deletion. So if we wanted to encrypt a message M, so this scheme will be to encrypt 2 bits of message. We will send these conjugate coding states, the four qubits, and then we XOR M with the substring rcomp. So of course here we have rcomp of length 2, which is fortunate for this application, and we use a one-time pad. So we're going to use rcomp as the key basically that encrypts the message M. From here, So from here we can talk about the deletion procedure. I have said that the message is encoded with the one-time pad rcomp, which is a substring of all the qubits encoded in the computational basis. So what about the qubits in the diagonal basis? Well, they're going to be used for the proof of deletion. What happens when you have a qubit that's in the computational basis, but you measure it in the diagonal basis? We've seen this in the BB84 example where Eve was eavesdropping, for instance, or also in the quantum money when we had some strategy. So measuring in the wrong basis is going to output a random bit. In other words, if B was encoded in basis 0, and you go and encode, and then you go and measure B in basis 1, you've actually deleted that bit B. You don't have access to it anymore because you've measured it in the complementary basis. That measurement result returned a random value, and the original value B is lost. So let's take advantage of that in the certified deletion. The other aspect of which we take advantage of is if you measure the qubit that's encoded in basis 1 and you measure it in basis 1, then the outcome is deterministic. You know that you should observe the value B equals 0 or B equals 1. So let's take advantage of that and to delete a message, the recipient should measure all qubits in the diagonal basis. Okay, remember the actual message was encoded in the computational basis. So if you measure all qubits, including the ones containing the message in the diagonal basis, you've deleted the message. But then how do you know that you've deleted the message? Well, if you've measured honestly, then these outcomes of R diag are deterministic. These qubits were encoded in the diagonal basis. So this substring should absolutely be 1 and 0. So the stars represent wildcards, so we don't care about these 2 stars, and the 1 and 0 should absolutely be 1 and 0 if the parties have been honest. So to verify, we verify this R diag substring. And to decrypt, so back to the honest case, what's the decryption key? Well, it'll be theta, and once you know theta, namely like the combination is revealed, you measure all the qubits where position theta is equal to 0 to get rcomp, and then that gives you the rcomp substring, which is used in the one-time pad, and then you can undo the one-time pad, and you'll get the message M. So the proof intuition, actually, the most of the work okay, well, first we had to come up with this idea, this scheme, and then most of the work to prove security was to, well, define it, which is coming up, and also to map it to the adversarial model in quantum key distribution. And turns out that that worked after a few iterations. And then we were able to use the techniques from quantum key distribution. We could have used sampling. Actually, some follow-up work has used sampling as the application that I showed earlier today. Here we use the entropic uncertainty relations that had been established previously. And intuitively, what happens is that if you look at different attacks of the adversary, as the probability of correctly predicting R diag increases, namely convincing the sender that the message has been deleted, then the probability of guessing R comp, which is required in order to guess the message without knowing the key, well, that probability is going to go down. And we see this in actually regular Heisenberg uncertainty relations, and these entropic uncertainty relations are particularly well suited because they work with min entropies, which are the similar concepts that we had for quantum key distribution. And maybe I'll just gloss over this. It's the definition of security for certified deletion, like what you would have to prove. And basically, it's bounding the probability that the adversary is able to decrypt and at the same time convince the sender that the message was deleted. And as long as we're able to bound this probability to be small, then we'll say that the scheme is secure. The proof, no big surprise, is also going to purify the protocol and go to an entanglement-based version and analyze that row ABE state that the adversary has prepared using this and end up being able to apply these entropic uncertainty relations. And let me mention that thanks to the approach that we took for the analysis, the noise-tolerant techniques that are known for QKD are also applicable. So we're able to get this single qubit prepare and measure noise-tolerant property that is the one that is most relevant for current technology. And there's lots of follow-up work on certified deletion. Let me mention this one, and then there's also more. This slide is slightly out of date. So so this idea of the recent work on quantum cryptography that using advances in classical cryptography has been really useful for the certified deletion, for instance, where we're able to make certified deletion, apply certified deletion to all sorts of new functionalities. So certified deletion for public key, attribute-based, classical, and classical communication, for instance, for this work that I'm citing. So that brings me to the end of the tutorial. Thank you very much for your attention. Here are some references. I've already mentioned some as we were going along. And so for your future reference, here's some of the related papers. Thanks a lot.
Do you have any further questions from the audience? All good?
Can I?
Yeah, please.
Yeah. Hi. You said for the deletion that you show like a trade-off, that the more you can prove that you deleted, the less you can reveal, even given the key. The keys are comp, right?
Without the key, the more
like
more you can prove deletion, the less you can decrypt without the key.
Without the key. Okay. So why is that better to use that thing rather than just don't send the key and then that's it?
Thank you. Thanks for correcting me. Okay, so the correct statement is So they do get the key. Okay, I got confused with another thing that I didn't present. So the more you can convince produce the valid proof of deletion, the less you can decrypt, even giving the key. So the key will be revealed, and then we're saying that if you've deleted, you've irrevocably lost your possibility to decrypt, even when the key is revealed.
Right. So I think I didn't understand. I didn't understand how, because I thought you have the quantum part and the classical part, and in the classical part you just have the message X or the key. If I get the key, what do I care what happened to the quantum part? I just
Okay.
XOR with the key.
Yeah. Okay. So I did call this the key. Where is it? RComp.
Yeah.
Okay. The point is that RComp is not sent in the clear. It's in the original encoding. It's sent as this substring of this sub quantum system. Eventually, when the key is revealed, it's not RComp that's revealed. It's theta. So this is for the correctness to decrypt using the key theta. So maybe I talked about two different keys, but the key for the certified deletion is theta, and this RComp is used as a building block as the one-time pad key, but it's not the key of the certified deletion.
But the one who sends, like Alice, not the lawyer,
Mhm.
she has everything. She has our comp, basically, right?
Alice as a sender, yes. The lawyer in my example is actually the recipient.
Yeah. So in the world of trying to say that this person, the lawyer, cannot ever understand what was happening because she proved to us that she bombed the
Deleted. Yeah.
blew up the message, but if she ever gets our comp, she can.
Yes, because our comp is classical, and the lawyer could store MX or R comp. Yeah.
Right. So I'm a little bit unclear of what is the guarantee.
Okay.
Like,
So like the reason that R comp is never going to be revealed, condition on the proof of deletion being accepted, is that the proof of deletion in the honest case, and then we're able to show that the dishonest case can't do anything much different, is that when you go and measure everything in the diagonal basis, which is required to delete the message, then you've actually erased the information about RComp, because you've actually measured ket 0 in the diagonal basis, so it's like gone, and ket 1 also, if you measure it in the diagonal basis, it's gone.
yeah. Okay. Maybe I'll ask.
Okay.
You.
Hello. Here.
Yes.
So you said that for the certified deletion, so there is sort of a mapping to adversary in QKD
Mhm.
or to do the proof. So I'm just wondering. So this is like a one-way mapping, right? Or does it
Oh.
imply that if I have a QKD sort of setting, there is an equivalent certified deletion protocol that I can construct from that?
I don't think anybody has answered that question in full generality. I would suspect maybe yes.
Oh.
I meant at the level of good enough mapping that you can apply a security tool.
Okay.
Yeah.
And then maybe just a quick follow-up. So here it's sort of like you need to really know like the state and the measurements you're doing, I guess. I guess I wanted to just think of like, again, with this mapping. So if I have a device independent way of doing things, then does the proof again map to like, I don't know, like, yeah, again, the mapping between a QKD and certification.
I like that type of stuff. That's
Yeah.
what I do for a living.
Okay.
So, I mean, I'm definitely learning. And there is a paper on certified deletion with device independence. And that's a good question. I'd have to double check. I would suspect that yes, they end up being able to reduce to device independent versions of device independent QKD. Yeah, that's my first guess.
Okay. Okay. Thank you.